Hello everyone, I'm Kuromeru. Today, we will learn about active and passive transformations. Our goal for this lesson is to understand a unified approach to transformations, including scaling, rotation, and the Lorentz transformation, since the direction of rotation and other aspects can often be confusing. This topic tends to cause some difficulty, however. By going through this lesson, I believe you will no longer feel confused. Now, let's get started. Let me explain the essence of this video. It is to express the vector v with a basis as follows. Its meaning will gradually become clear throughout the upcoming video series. A good example to explain the active and passive transformations of a point is scaling. For instance, the active enlargement m2, which doubles the distance from the origin, can be written as follows. Using the notation from earlier, this can be expressed as the following operation. This doubles the length of the basis vectors. The key point is to consider the scaling matrix M2 acting on the basis vectors Ex and Ey, since this transformation actually moves the point itself. It is called an active transformation. So, what is a passive transformation? Instead of moving the point itself, we measure it using a newly generated basis, which gives us new components x' and y'. In other words, it works like this. The vectors before and after the transformation are set equal to each other. From the perspective of the transformed basis, the same point appears to have half the original distance. In passive transformation as well, the key point is to consider the scaling matrix M2 acting on the basis vectors Ex and Ey. In this way, we can interpret an active transformation as replacing the basis with a new one, while a passive transformation is remeasuring using the new basis. Since one corresponds to the other in this manner, we can see that they are inverse matrices of each other. Have you noticed that in both cases, the new basis is obtained by applying M2 to the old basis? Now, a counterclockwise rotation r theta about the origin can be written as follows. For an active transformation, we multiply the basis from the right by r theta, expressing it in this form. It is common to interpret this as an operation acting on the components. This is what we call an active rotation. Next, let's look at the passive rotation. Just like in the case of scaling, we have the following equality. The components measured in the new basis behave as shown in this animation. This is what we call a passive rotation. Now, let's consider the active Lorentz transformation. The concept of an active Lorentz transformation is not commonly discussed. When we set eta such that hyperbolic tangent eta equals v over c equals beta, we define the active Lorentz transformation t eta as follows. Here, we have the unit vectors et and ex of a stationary inertial frame. This transformation replaces them with the unit vectors et' and ex'. of an inertial frame moving in the positive x direction with velocity versus over c. This is what we call the active Lorentz transformation. Finally, let's consider the passive Lorentz transformation. This is the well-known Lorentz transformation. It is represented by the following inverse matrix. The transformation can be visualized as shown in this animation. This is what we call the passive Lorentz transformation. In summary, both rotations and Lorentz transformations start with an active transformation of the basis. I hope this helps deepen your understanding. That's all for today. If you enjoyed this video, please subscribe to the channel and give it a like. Your support motivates me to keep creating more content. Thank you for watching.